In many everyday situations, we spontaneously use our memories to guide our actions. Take cooking, for example. You use your eyes to sample the recipe. Then, you encode the instruction of adding flour to a mixing bowl into what we call working memory. You then use that information in mind to search for the flour. There's no single way to follow this recipe. Everyday tasks like this offer a high degree of flexibility in how we carry them out. For example, once you've found the flour, you're faced with a decision. Do you rely on memory to recall what to do with the flour, or do you first check the recipe again? Tracking such flexibilities of free-flowing, naturalistic behaviour is not trivial. To solve this, we developed a virtual reality task designed to mimic memory use in real-world situations. The task requires participants to replicate a model arrangement by selecting objects from a resource table and placing them in the corresponding spots within a workspace. Importantly, compared to traditional memory tasks, participants could freely structure their behaviour. This freedom is important because it's representative of our flexibility in coordinating when to sample new sensory information and when to rely on memory to guide behaviour. We constantly decide what to sample, how much, for how long, and how often. At the same time, we determine which and how much information to use from memory. To complicate matters, our memories usually span different timescales. If, instead of a brand new recipe, you're cooking your favourite dish, past experience or long-term memory comes into play. Yet, little is known about how long-term memory influences how we rely on memories in naturalistic settings, particularly how it shapes the coordination between sensory sampling in service of encoding and using available contents in memory. For example, would you memorise more steps from the recipe at once if you've cooked it before? Do you look at the recipe less often? To investigate how long-term memory shapes this flexibility, participants learned a set of arrangements by practicing them multiple times, similar to cooking the same recipe repeatedly. The next day, they returned to complete these familiar arrangements, interspersed with new ones. This design allowed us to compare conditions where participants could rely solely on working memory with conditions where they could draw on both long-term memory and working memory. We find that long-term memory facilitates spontaneous memory usage through multiple pathways. Overall, when cooking a familiar recipe, our participants executed more steps in a row before referring back to the recipe. That is, if we have available long-term information, we can save ourselves some effort of checking the recipe constantly. More so, when consulting the recipe, our participants spent less time looking at each step before executing it. That means that long-term memory made sensory sampling more efficient. So, interestingly, increased reliance on memory did not coincide with sampling more sensory information. Instead of sampling more information from the recipe, participants used it directly from long-term memory. So, they managed to add certain ingredients into the pot without needing to check the recipe at all. Overall, we demonstrate that tracking freely unfolding, memory-guided behaviour across multiple timescales is feasible. We find concurrent, spontaneous deployment of multiple long-term memory mechanisms alongside working memory and sensory processing. Our results emphasise the importance of considering the complexity of flexible behaviour to understand how memories from different timescales are engaged interactively to guide our actions.